and the information is needed. But okay, there it is. Okay, so I'll do a quick recap. This is what I covered on Tuesday, because today is Thursday. Okay. Because I'm like, what day was that? It wasn't today. Okay, this is what I covered for on Tuesday. And I was essentially saying that this chapter is a little challenging in the way the notes are written. My personal opinion is that the chapter is a little bit random, no pun intended. But what I was talking about on Tuesday was that as you're reading through, make sure you're taking notes. Take notes in a way that makes sense to you. Write things down in a way that makes sense to you, so you're able to navigate through the information carefully. You can see all these notes I write, right? I know the issues I have. I'm very distracted, I'm very excitable. So it doesn't take much for me to go off on a tangent. And so I do a lot to make sure I'm keeping up with the information, including writing all over the stuff I'm reading, right? So as I was reading this, I was trying to kind of make up a list. When one of the questions you'd be asked, and which, as you're learning the chapter, you can kind of learn with the goal in mind, which is what kind of questions will they ask me? And as you're learning the chapter, you're learning it trying to prepare yourself to answer those questions. Those questions are usually in the learning goal at the end of the chapter. They usually say, this is the learning goal. Paraphrase, we will ask you these kind of questions, right, over these topics. So one of the things they're going to ask you in this is, what is the criteria for greater entropy? So they'll give you a question. I can use purple. They'll give you a question where you are supposed to judge if the transformation, it can be a physical one or it can be a chemical one, is increasing in entropy. So what I mentioned on Tuesday was, do not confuse entropy with spontaneity. Why am I saying that? Because I did that. Okay. So I'm like, spontaneity starts with the letter S. So delta S must be about spontaneity. Now, does increase in entropy ultimately, in the end, lead to an increase in spontaneity? Sure, but entropy is just part of the story. It's not the whole story. So, what I'm trying to say is, there is no direct correlation between an increase in entropy and an increase in spontaneity. Entropy is just part of the story. So I won't go into all this part here because I already recorded that before, but let me see. Yeah, so before I continue with this part here, did you go over how to determine if a reaction is spontaneous?
Yes.
Okay, great. So the one with the universe, did you do that part?
Wait, let me see.
With Delta S universe?
No, I didn't.
Okay. So before I get into this one right here, well, let me cover this and then I'll kind of slide that in and then I'll continue. Okay. So we'll cover this part first, and then when we're done, we'll talk about criteria for spontaneous reaction, because it's not the same as a criteria for greater entropy, right? Because when I was studying this, that was the back of the head connection I was making, and it was not the same thing. And so I'll get some questions wrong, and I'm like, what am I missing? And then fast forward later, I realize, oh, in my head, I'm connecting S with spontaneity, but it's not. Okay. When we're looking at entropy, entropy is the thermodynamic function that measures disorder. And disorder is all about randomness. And to me, disorder is fun, energetic. Anything that is chaotic is greater disorder, right? As we're looking at a chemical reaction, or a physical change, we want to know if the change is going from a lower disorder to greater disorder. So here we have a criteria for greater disorder. So all of these should go from low to high, right? Disorder. But when you're measuring disorder, you write down the value as entropy. Kind of like when you're measuring how heavy something is, you write down the mass. So when you're measuring disorder, you write down the entropy. So we're saying for all of these transformation, Delta S is positive. So when you have a solid molecules which are very ordered, organized, tight, right? Because the molecules have very high intermolecular forces. If they're transforming to become a liquid, and we don't really know what the process to go from solid to liquid, it could be higher temperature, it could be just a lot of different things, a change in pressure. We don't know, and at this moment, we honestly don't care. All we care about is a change going from solid, more organized molecules to liquid freer molecules, you have a greater entropy, greater disorder, right? These are physical transformation because all we're having is the molecules moving a little bit further apart from each other. From liquid to a gas, same thing. The liquid molecules are held a little bit closer to each other compared to gas molecules. Gas molecules remind me of youth. When I say this, I know I sound old. You're free, you're not encumbered or entangled by life responsibilities. You're living your best life out there, very low intermolecular forces to hold you down, right? And the gas molecules are moving around freely, and essentially that freedom makes them more random, right? So once again, going from being encumbered to being unencumbered, more freedom, from less freedom to more freedom, delta S is positive. Okay. When you're looking at, so the last, yeah, the last three, once again, when you're looking at these, you want to look at the balanced equation, technically for all five, right? So you're looking at the reactant side versus the product side in each case. You're going for number three, you're looking at increased product molecules. The molecules can be solid, liquid, gas, but I'll tell you something. With this one here, the easier one to see is if you have greater gas molecules in products. Okay, so if you have a greater number of gas molecules in the product, remember the existence of a gas molecules by a molecule by itself means greater entropy because those molecules have got more motion, okay, more freedom. So if you went from a situation where your reactants have less gas and then they form a product that has more gas molecules, then delta S is positive. What about increasing in temperature? Okay. Increasing in temperature, you're increasing the energy, right? I don't know why. I I don't know if it's I want to think of it as a bad habit, but it's just when I'm learning, I like to associate as quickly as I can. I like to associate. When I'm thinking increasing in temperature, I'm thinking increasing in energy. You go to a room like a gym where there's a lot of movement, a lot of energy. That kind of environment, greater entropy, right? So as you increase the temperature, or a party that's really, energetic, greater entropy, lot of energy, right? When the molecules have more energy, they have more freedom, they have more movement, greater entropy. Okay, dissociating solid. For example, you take table salt, that's a solid, you put it inside of water, and then you get the ions dissociate. Ions are formed from what used to be a solid. First of all, look at that. We're getting more products, right? You had one unit here, one entity. It broke apart to make two, double what you used to have. More product, they're more free, more motion, greater entropy. Okay, so as the chapter continues and continues to unfold more things, it keeps telling you newer things that indicate greater entropy. So I think that as you're journaling your notes or writing your notes or whatever, however way you keep information, you want to kind of have a list. It helps when you're solving these kind of questions to go back to that list. It helps you to learn that list and see them, these concepts together as a list. How is it unfolded in the chapter? Bits by bit by bit by bit. But when I like to learn it, when I like to review it, I like to review the parts that fit together at the same time, like I'm showing you right now. Okay? The same thing with criteria for spontaneous reaction. Do they tell you this criteria in a list? No, they don't. What do? Reveal it a little at a time, right? There are times when that irritates me. Then I remember, oh my goodness, chemistry, mystery, heavy on the mystery about the chemicals, right? It's like watching a series on TV where they're telling you a story about an individual, the main character. They don't tell you everything at once. They show you a little bit in season one and in season two, something comes up that reveals more about it. So that's kind of how this information is unfolded in this chapter. Everything isn't given to you in list form, but when you're reviewing, you want to pack it together back to back to back, kind of like binging on Netflix, right? You want to pack it that way because me personally, I feel like I remember things better when they're connected versus when it's spread out. Okay. So I like to go through and write the criteria for spontaneous reaction. The first one they revealed was the delta H value in combination with delta S value. They said delta H has to be negative sign. And this was said back in some of the slides in the back, okay? And then this is in combination with delta S being positive sign. They said nothing about the magnitude. They don't care about the size, just the sign. So when delta H is negative and delta S is positive, these have to be a combo. You're judging a chemical reaction or some kind of transformation, a physical transformation, and you're able to decipher from that transformation. Delta H is negative, delta S is positive. If you come to this conclusion, that transformation is spontaneous in those conditions. Okay? So they unfolded that in the past. The second thing they unfolded was judging spontaneity from the point of view of delta S of the universe. Oh, so I need to specify something here, right? Which, as I said, this chapter is not the easiest to understand. Some of it, I blame it on how it's communicated. But I've realized in life, since I am a chemist and I do work with other chemists, sometimes it's hard for them to get the words out. I'm like, is this what you mean? Is this what you mean? And then eventually, like, oh, this is what you meant. Why didn't you just say it that way? Right? When they say delta H here, it's implied the system. Delta S here is implied the surrounding. So, sorry, it's still the system, right? These are both the system. And then delta S here is of the universe, right? So in these first two here, the system is talking about the chemical reaction, and that's what we're talking about. Delta S here is for the universe. So in this second scenario, you're making a judgment of a transformation that's taking place, and you're about to decide, is this spontaneous or not? Delta S of the universe has to have a positive sign. So I'm paraphrasing what they said. You look at it, if they give you the delta S of the universe sign, they will have to specify universe. Universe cannot be implied. It's too great to be implied. So that will be stated. Delta S of the universe is positive. And if it's positive in your mind, you say, oh, they're trying to communicate this reaction is spontaneous. Okay? But what if they don't give you delta S, the universe directly, and they give you a means to calculate that? Where is this one right here? If they give you a way to calculate it, the formula we have to figure out delta S of the universe is delta S of the system plus delta S of the surrounding. Okay? So, in the world of chemistry, the universe is broken down into two components, right? You have the system and you have the surrounding, and together they make the universe. Very simple. This is sort of a very simplified view of what the universe is. It's not the stars and the moon and everybody in it. No, no, no. System, surrounding, equal universe. So if you can do whatever you can do to make sure the universe is delta S of the universe is positive, you can make that reaction spontaneous. So before I continue where I left off, I'll say here, since delta S of the universe is obtained by adding delta S of the system, and by the way, the system is also the reaction, The surrounding is, well, everything that's not the reaction. So the surrounding is, I guess I can say here, the environment. Which, what exactly is the environment? They would define it in the question, sort of, right? So you have the chemical reaction, you have the environment around the chemical reaction, which is in contact with the chemical reaction. And essentially, when you get a delta S of the reaction, delta S of the surrounding, and then you add them, you get the universe. To make transformation, I'll keep this generic, transformation spontaneous, okay, comma, make delta S of the universe positive. Okay, so let's see conditions in which delta S of the universe is positive. So I'm going to kind of break this down differently than I did on Tuesday. Universe. If delta S of the system, I'm going to assign numbers. So delta S of the system is, delta S of the system is, let's say, positive 5. And the units for S is joules per Kelvin. So positive 5 joules per Kelvin. Delta S of the surrounding is, oops, this needs to be in the bottom, is positive 10 joules per Kelvin. Then, if these are the values, all I have to do is add these, positive 5 joules per Kelvin plus positive 10 joules per Kelvin, and positive are positive, right? So I end up with 15, which is positive joules per Kelvin. And if I have those numbers simply, I can conclude when the system's entropy change is plus 5 and the surroundings entropy change is plus 10, then the universe entropy change is plus 15, and therefore this reaction is spontaneous, right? Right. I mean, it's like very straightforward, very simple, right? If only chemistry was like that. Now let's dive deep and explain what happened. Was it in February to Texas? What happened to Texas in February? So in February of this year, which I explained on Monday, I like telling that story, so I don't mind telling the story again. Sorry. No, you know what happened. You know what went down. It snowed. Okay, they said it in the news, but we never trust the news people. It snowed. So what exactly happened in February? It snowed. And not only did it snow, it snowed spontaneously. You know, I had to bring that in there. Yeah. I mean, it was a hard winter, but it was spontaneous and nobody could stop it, right? We didn't have to encourage it to happen. It wasn't spoken into being just because the what's it called? The the whether people spoke it, that didn't make it happen. It snowed spontaneously. So what conditions encourage the snow to form spontaneously? So let's go ahead and analyze this because it is part of the lecture in there in the past. Okay. So for it to snow spontaneously, we are going to examine the delta S value. To snow spontaneously, comma, delta S of the universe has to be positive, right? That's the bottom line. It has to be positive. Well, how do we explain how it's positive? What is snow exactly? Snow, how is snow formed? Snow forms, so snow forms in a low temperature, what we call freezing temperature. Okay, so that's the first condition. Snow forms in a low temperature. So low temperature is required. So apparently when we're saying it snows spontaneously, what I'm trying to say here is snow spontaneously at freezing temperature. So freezing temperature is required. And then we'll go into all of this. So let's pick a temperature that actually happened. Okay, it went down to like where I live, 9 degrees, 10 degrees. I never experienced it myself because I was stuck inside looking out the window. Okay, so the temperature was let's say 10 degrees Fahrenheit. Was it Fahrenheit? Yes, Fahrenheit. Cold. Okay, so we'll come back and examine it because it is part of the lecture. Number two, what was the physical transformation? The transformation we saw when the temperature dropped that low was liquid became solid. Okay, so liquid became solid. When a liquid becomes solid, a liquid has a greater entropy and a solid has a lower entropy. Okay, so technically we're saying we went from greater disorder, right, to more order. So the transformation of a liquid becoming a solid is actually delta S that's negative. It decreased in entropy. So the day it was freezing and we were at home so cold trying to, if you still had power, it was just so much going on. Very random, right? When all this stuff was going on, we actually had a decrease in entropy. So from liquid to solid, we end up with a decrease entropy of system. So what I'll say here is delta S of the system ends up being negative. Okay, but we also know that if a solid becomes a liquid, as in melting, in order to take a piece of ice and melt it, you have to somehow apply heat to it, right? For solid to become a liquid, you have to add heat. Okay, we understand that part. That means, i.e., for liquid to become a solid, it has to lose heat. Okay, so this is the scenario we are looking at. This is what happened, all in the temperature of 10 degrees Fahrenheit, which was very cold, not just cold, super cold. So when snow was forming, when snow was forming, comma, liquid water lost heat to the environment as it formed snow, right? From liquid to solid, it has to lose heat. So this happened. So the environment takes the heat then. The environment is just kind of neutral, sitting there just waiting. Okay? So the environment, aka outside, absorbed heat. So remember, the environment is the surrounding, right? So the environment slash surrounding absorbed heat and increased temperature, right? So we're kind of remixing what we just learned. We just said earlier, anything you do to increase temperature does what? Increases the energy, which does what? Increases the randomness. So as the surrounding absorb the heat from the water, it increased temperature and increased entropy. So while the water was losing entropy, the surrounding was increasing entropy. And because the surrounding started at such a low temperature, it increased the entropy by a lot. So increased entropy by a lot. So let me try to map this out mathematically. Okay. So let's say it's freezing. All we know is we're inside, we're cold, we're shivering. Meanwhile, in the world of thermodynamics, this is what's going on. Liquid is becoming a solid. Delta S is -5 joules per Kelvin. And then as liquid becomes a solid, heat is lost to environment. We got that. Environment uses heat to change entropy. So now entropy. This right here is the system. And this is now what's happening in the environment, which is the surrounding. So remember, the environment is the surrounding. So in the world of the surrounding, after it gained heat, what transformation do we see? The surrounding gained heat, and therefore its delta S is bigger and positive joules per Kelvin. This is the surrounding, and this is the system. The system lost entropy. The surrounding took the energy from the system and used it for its own personal gain. Not really personal, environmental gain, I don't know. But you understand, it took the energy that was discarded by the system and then increased its own entropy. Well, we have to figure out delta S of the universe. The universe delta S is the system's delta S, system, plus the surrounding delta S. What was happening that cold week or days in Texas was the system was around, these are made up numbers, -5 joules per Kelvin. I don't think anybody was calculating this, plus 20 joules per Kelvin. And when you add this, you get a total of 15 joules per Kelvin. And guess what? When delta S of the universe is positive, it spontaneously froze. And they could do nothing to encourage it. It just happened. The environment temperature dropping so much allowed this to increase so much. So the environment temp dropping so low allowed for this to increase so high. If the temperature of the environment was around 50 degrees, this may have increased, but not high enough, right? So the surrounding, when the system is releasing energy to the surrounding, the entropy of the surrounding will always increase. The question is it increasing high enough to kind of overcome the negative in the system? That's where the conundrum lies. If it's not increasing high enough, then nothing will happen. You can't freeze, have snow in regular Texas weather when it's like 50 degrees Celsius. You can't, because the environment temperature is very high to begin with. And when it's very high, the increase you have here may be like +3. You take -8 plus 3, you get -2. You need the overall entropy change of the universe to be positive. It's not really even about the sign, it's just positive for it to be spontaneous, whatever it is you're looking at. So, of course, regular day, well, not regular day in Texas, temperature very low, allow for this side of the equation to get very high, and then it froze. And of course, we're running around trying to look for electricity, heat, and water, and food, and yeah, you know the story, you know how it went down. Yeah, so a day like that can be explained by thermodynamics, at least that world of people. So over here, of course, this is now, as you're looking at these problems, we're going back to looking at, once again, they're asking you to predict the sign of entropy change. Entropy is the reaction level, like the detail level of the reaction, versus spontaneity is more like the holistic. I mean, theoretically, they're both holistic. I'm trying to think about, but entropy is talking about randomness, right? Predict the sign of delta S for each process. If you look at this first one, gas, greater random, liquid, less random. So this is going down, right? So delta S has to be negative. Solid carbon dioxide is subliming. Subliming tends to be going from a solid directly to a gas. What is that? Gas. There. Okay. Solid has lower entropy. Gas has the greatest entropy possible. So we're going up. So the change here in entropy is going to be positive, right? And then here, oh, look at that, this scenario here. We got how many? 2 molecules of the reactant. We got 3 molecules of the products. And you see how they're all gas? So it's okay for me to compare gas, 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 gas. So we have 2 total here, 3 on the product side. So you went from lower to higher. Therefore, delta S is positive. Okay, so they go through and they explain all that stuff here, and you can practice some more of these other ones here, which I won't do right now, but you get the idea. So here they go into more details, explaining what I just explained right here. They go into more details. It's just pretty much what I said, but in their own words. That the explanation I gave you that explained why that explained why it snowed on that fateful day is once again because the change in even though the change in entropy of the system was negative, the change in entropy of the surrounding was positive and large. That's the secret combo you need. If both the change in the system and the surrounding are positive and positive, that's no big deal because if it's positive for system and positive for surrounding, it will be positive for the sorry. This is supposed to be universe. I wrote system here. It'd be positive for the universe, right? Yeah. If it's the system is positive, surrounding is positive, universe will be positive. That's a no-brainer. That's like, okay, positive plus positive gives you positive. The issue comes up when it's negative for the system and it's positive for the surrounding. And the goal is to make it spontaneous. The surrounding has to be positive and large to kind of cover the system and then make this positive. Now, what happens if both the system and the surrounding are negative? Then the universe will be negative, and that's a situation, whatever transformation you're looking at, will never be spontaneous. It can be spontaneous in the reverse, because reversing the reaction will probably reverse the signs, right? But the way you're looking at it, it will not be spontaneous. So in this first situation here, if both the system and the surrounding, if the system and the surrounding have negative change in entropy, the universe will also be negative. Okay? So this is not going to work. If the system and the surrounding are both positive in the changes in entropy, the universe will be positive. If the system is negative and the surrounding is positive but large, the reaction will be spontaneous. So let me add this. If the system is negative and the universe is, sorry, system is negative and the surrounding is positive but small, then this will still be negative, and so this will not be spontaneous. I write here, not spontaneous. Spontaneous. Yeah, that. Okay. So that's kind of laying everything out. And then they say it out in words here. The entropy increase. Yeah. So it says here the second law demands that the entropy of the universe increase for a spontaneous reaction, any spontaneous reaction. However, processes like condensation of water vapor are spontaneous even though the water vapor is more random than the liquid water. If a process is spontaneous, that means delta S of the universe is positive, yet the entropy change of the process is unfavorable, that means delta S of the system is negative, there must be a large increase in the entropy of the surrounding, meaning delta S of the surrounding has to be positive. Okay? Therefore, they summarize the entropy increase must come from the heat released by the system. The process must be exothermic. So when the system is going from being more random to less random, it has to give up the energy, right, to become less random, aka boring, in my opinion, right? I'm like, okay, you went from being random and cool to be boring. That means you lost some energy, right? So the surrounding is like finders keepers, takes up that energy, and then it increases its randomness. In doing so, the entropy of the surrounding increases. If it increases high enough, the whole process becomes very spontaneous. Okay? So they kind of go over it again here. I talked about this, so I won't go over that. The thing they mentioned here, the higher the original temperature, the less the effect of the addition or removal of heat. So if the environment starts at a lower temperature and it absorbs energy from the system, its randomness increases by quite a bit. But if it starts off at a high temperature, the change is not that significant. Okay? So here is where we're going to mathematical parts. So let me go ahead and go over this. I wrote on this on Monday, but I'll write over here. So here they're saying we're going to quantify the entropy changes in the surrounding. So we know the surrounding is kind of the responder, right? The in this story here, the surrounding is not the initiator. The initiator is the system. The system does something and the surrounding is just kind of passive, like I'm just waiting for heat from the system. I'm just here surrounding, right? So the entropy change in the surrounding is proportional to the amount of heat gained or lost. Okay. So even though in this equation they're making it sound like the surrounding is the initiator, no, the surrounding is just responding to the system. So we can look at this equation here or this relationship here as the surrounding gained heat. Remember, heat, the symbol for heat is Q. So Q is heat. But we know the surrounding gains heat from the system. There's only two parts in the universe. So if the surrounding has heat, you know the heat came from the system, right? So the surrounding gains heat. So if you're wondering, how did I know it was gained? The nothingness here means it's positive. If it was negative, the negative will be indicated like we see on the right side, right? This is negative, this is positive. So positive means gains, right? The surrounding gained heat. So I'm interpreting this symbol here, but you know who gave the surrounding heat. The system. The system lost heat. How do I know that? Negative means lost. So whatever the system is discarding, the environment is gaining or picking up, right? Because in the universe, according to this chapter, there's only two components, two major components that we're focusing on. The entropy change in the surrounding is also inversely proportional to the temperature of the surrounding. Remember, temperature. So weirdly enough, when I was learning this in school, I think I memorized some of this stuff. I don't know, it's just it was the time, it was the age, it was a lot of things. Okay? And I just memorized this relationship right here. I memorized this relationship. Okay? So we're talking about trying to get the surrounding entropy to be big. So the surrounding entropy is influenced by two things. Okay? So actually, let me try to summarize here. Entropy of surrounding, so I'm paraphrasing what they're saying, is influenced by, I have my iPad and my book and it's making my handwriting a little bit extra sloppy, by A, QSYS, heat of the system, I should say heat from, not heat of the system, heat from, yeah, heat from the system. Okay, so the surrounding doesn't gain the heat from the system if the system doesn't lose it. So that's why I change it from of to from. Whatever the system is discarding, the surrounding is picking up. So imagine spring cleaning, only the thing that's being tossed out is heat, right? If the system loses heat, the surrounding picks it up. B, temperature of surrounding. So these two things influence the entropy of the surrounding. And how do we know that? The mathematical relationship that's shown to us right here. The surrounding is influenced by directly by the heat lost by the system divided by temperature. Now here they don't really say temperature of what, you can say the surrounding, but whatever temperature they give in the question, that's what it is. And this temperature has to be in Kelvin. They didn't say that here, but it's supposed to be in Kelvin because in the end, the units for delta S will be joules per Kelvin. Okay? Okay. So based on this relationship, what can we say about the relationship between delta S surrounding and system? Because these have a numerator relationship, they have a direct relationship. So the Q of the system affects entropy. So I'll say here, what do I write here? Direct relationship, right? They said it in the text before or they implied it, but here I can see it mathematically, right? Because you can see how they are both numerator. Then the denominator, because you have a numerator denominator relationship, I'm using the wrong marker thing here. Then you can see this one here is indirect or inverse, indirect or inverse. What does this mean? If the temp of surrounding is small, comma, the delta S surrounding will be large, right? Because that's what inverse relationship is, small and large. Isn't that what I said before in so many words? Yes, it's been said over here, right? If temperature is small, then delta S surrounding is large. That's why it freezes on a cold day, because on a cold day, temperature of surrounding is small with low, right? But it won't freeze on a warm day, a regular Texas temperature, because in that warm day, the temperature will be too high. When this bottom part gets too high, delta S surrounding is not high enough. It influences this, and then therefore we don't get a positive delta S for the universe, and then nothing happens. And then we're like, oh, it never snows in Texas. It's not personal. The temperature of the surrounding is still high, right? Which we don't say that way. We're not like, well, sis, the temperature of Texas is, of the surrounding is still high. What we say is, it never gets cold in Texas. What we mean is the temperature of surrounding is always high, is never low enough to make this very high. I really wish we could communicate this way. I know nobody will communicate that way. People will be like, we don't want to talk. I personally think it would be more fun, but it's okay. You can't win all the time, right? I try to tell jokes. Somebody said to me, "Oh, you shouldn't feel bad about giving speeches. You can give tell people those dry jokes you have." I'm like, "Nothing about my jokes is dry. Those jokes are very funny." He's like, mm. I don't get why they don't get my humor. It's their problem. They should get they should learn thermodynamics. I'm like, no, I have a lot of humor though. They didn't think I think that they were laughing at me, not laughing at my jokes. That's okay. That's okay. So in this problem here, we are getting to apply that calculation, which is now you want to make sure once again, I keep saying the system is the reaction because it took me a while as a student to recognize this, right? Because for me, I have to make the right association. I like to learn by association, but I have to make the right connection, right? Or it messes me up. So it says here, we are calculating the entropy changes in the surroundings. Okay, consider the combustion of propane gas. So do I have, oh, I forgot that I had this written down here already. Let me just erase this. This happened on Tuesday. I've already forgotten Tuesday. Tuesday was another day, different day. But we're going to be working this out based on what we just learned, right? So here's the question. We're going to be figuring out the combustion of propane. So remember, the chemical reaction we're seeing is both the reaction and the system, right? So the system. So let's see. Oh, I provided this equation here. I need to provide the modified form of this equation. For in 1411, so Chem 1411, we learned that delta H over reaction is equal to Q. Okay, so we're picking up where we left from in 1411. Therefore, delta S of the universe can then be written as, I'm going to use delta H in the place of Q here, as negative delta H of the reaction over T. And remember, T has to be in Kelvin because delta H of the reaction is equal to Q at constant pressure. So I forgot to make that connection, okay? Because in this formula here, we know of Q. Q will be the heat. We know of temperature, temperature of the reaction, and we can use these two to get delta S in the correct units. But then we get to this problem right here, and the problem doesn't have a Q. It has a delta H of reaction. So how do you reconcile this? You remember in 1411, delta H of the reaction is the same thing as Q when the pressure is constant. So if you don't have Q and they give you delta H of the reaction, you use delta H of the reaction as you would Q. Okay? So I copy the equation over here. So delta H of the reaction is going to be like Q. And I can go ahead and write my equation. Delta S of the surrounding is equal to, in this case here, negative delta H of the reaction. Remember, the reaction is the system, right? Over the temperature. The temperature they give you here applies to both the system and the surrounding. Okay, so we're told calculate the entropy change in the surrounding. In other words, solve for this associated with this reaction occurring at 25 degrees Celsius. The temperature here has to be in Kelvin. So I'll go ahead and convert the temperature to Kelvin. This is 25 degrees Celsius plus 273.15. Okay, 25 plus 273.15. 298.15 Kelvin. Okay, so at least I've done the bottom part. Now the top part has to be, remember the units for delta S surrounding has to be joules over Kelvin. So I have to convert the top part so the unit is correct, right? Delta H of the reaction is currently given to us as negative 2044 kilojoules. But I need to convert this to joules. So 1 kilojoule is 1,000 joules. Ta-da! I get negative 204400. I need space. 0 there. Hold on. Those three zeros are, yeah, they look like three connected zeros. Those 000 joules, right? So this is what I have for my number. Okay, now I can then plug this into this part here, and I end up with delta S of the surrounding as equal to negative minus 204400 joules, right, over 298.15 Kelvin. Okay, I know for sure my delta S will be positive, right? But what's the number? So I'm going to plug it in my calculator, and here we are, 2044000. Oh, I just wrote the positive version of the number because you know it's going to be positive 298.15. And we get 2856 joules per Kelvin. Okay. And so delta S of our surrounding is positive. Can I judge this as large or small? I don't know. But let me erase this and then see. So I did part A of the question. That part is done. Delta S is surrounding. Part B of the question says, determine the sign. The sign is positive or negative, right? Positive or negative, not the magnitude, the value of the entropy change for the reaction of the system. So here they want to know, paraphrase of this question, is the entropy increasing or not? That's what they're trying to ask me, right? They want to know what the delta S of the system is. The system is the reaction. So I have used this already. I'm done with that. Now I'm going to judge the reaction as it is. All my chemicals on the reactant side are gases, good. All the chemicals on the product side are gases. So now I'm just going to use one of those many rules. Is it a liquid becoming a gas? None of that. Since they're all the same physical state, what I can do is then judge the number of particles, right? So coefficient here is 1, 5, 3, 4. On the reactant side, 1 plus 5 gives me 6 particles or molecules or whatever, just particle pieces, right? On the product side, I have 7 particles. So we went from fewer particles to more particles. That's a transformation, right? From left to right. So of course you have a delta S that is positive. The entropy increased because the number of particles increased. So you write here increase in particles. You can say moles or molecules. Particles is a more generic term that holds this and this. Molecules. If you want to be lazy, just say particles. If you want to be more specific, you can say molecules or moles. Okay? So delta S is positive. Then finally, oh, oops, wrong thing. Ignore all this. Okay. I am trying to make the same conclusions I made on Tuesday, but that's okay. So here it is. Part C of the same question. We're building up, right? Determine the sign of the entropy for the universe. So what I'm hearing is, what is S of the universe? Is it positive or negative? Paraphrase. Then they're asking you, is the reaction spontaneous? Of course, that answer will be tied back to the entropy change in the universe, right? Once you know if it's positive, it's spontaneous. If it's negative, it's non-spontaneous, right? Okay, let's see. We don't need the numbers in this case. All we need is the sign. So delta S of the universe is delta S of the system plus delta S of the surrounding. Okay, the system, oh, the system was a chemical reaction, right? What we just figured out here. System was positive. We don't need the number, right? If they gave us numbers, we could figure the actual value of this, but they didn't give us numbers. So what about the surrounding? Even though I have the number, all I need is the sign because I have to be consistent. So if the system is positive and the surrounding is positive, the universe is positive. That means delta S of the universe is positive and the reaction is spontaneous. Okay. I didn't like the conceptual part of this chapter in school. You know, you have your favorites where you learn something and you immediately receive an entropy boost. You know what I'm talking about? You feel so energized by the subject. You're like, yeah, this is my favorite. I feel like when I learned this when I was in school, the entropy level within me decreased. I just wasn't. Sometimes as a teacher, the people that taught this and this was their major and they did their doctoral thesis in this and that was their specialty, they weren't the most energetic people. I'm like, can y'all do something to increase your entropy? And here, I mean, like I like it's just it wasn't presented to me. And when I became a teacher, and I was like, how am I gonna do? How am I gonna show up with a higher entropy level as a teacher? Make this area boring. So as I and found different ways for me, it became more exciting. And so I'm hoping that this area is not as cumbersome, you know. I don't know if you have anything to compare it with. Like when you read it and you're thinking, this sounds like gibberish, that when I explain it, at least you feel like I have decoded it, right? My goal is to decode to explain versus to make it even worse. Yeah, it's just when the teachers were talking, I'm like, why though? Why can this not be more exciting? Okay. It's just most people I've seen who I met this lady once who did a PhD in this subject area. And I looked at her and I'm like, how can you? How could you survive 5 years of this? Five. And why you know more exciting? But I mean it can be exciting. It's just yeah. I mean, it's exciting when I'm reading it and making sense of it, right? So I don't know what kind of research she did. It is actually the actual area I would say is very interesting. It's just that sometimes the presentation is not the best. So you kind of have to read between the line and interpret it in a more exciting way, right? So yeah, after we did all that, then they keep talking about, I'm like, wait, I thought we just made this point, right? We just made this point that delta S of the surrounding is affected by the delta H of the system and the temperature. Right. So why are we trying to make this point again? I don't know why they do. They say when heat is added to the surroundings that are cool, in other words, the temperature here is lower, it has more of an effect on the entropy than it would if the surroundings were hot. They're just saying if the temperature is colder and the system is absorbed by the surrounding, then this is greater because the temperature is colder. This is colder and it goes with a greater value of delta S. But if the surrounding were hot, as in if T is higher because the surrounding is hot, delta S of the surrounding will have a lesser effect, will be is smaller. Okay, so you see how I'm paraphrasing what they're saying? I'm not just reading what they're saying, but I'm writing it in a way that makes more sense to me because I already got the point they were trying to make. So all I'm doing right now is just tying in what I'm learning to the point they already made because they're still going on and on about it, right? So water freezes spontaneously below 0 degrees. Just saying it again. In other words, temperature is low, right? Because below 0 degrees is very, very cold. Celsius, because the heat released on freezing, oh, reminding us, when freezing is happening, heat is released by the system, increases the entropy of the surrounding enough to make delta S positive. Delta S, they're referring to the delta S of the surrounding here. Okay, they're saying the same thing they said before. Above 0 degrees Celsius, they mean when the temperature is higher. How many times can they make that point? But hey, I'm reading on. The increase in the entropy of the surrounding is insufficient. So it's smaller, right? It's insufficient to make delta S of the surrounding positive. I think the delta S they're referring to here may not be the surrounding. They should have been more specific with that. I think they're talking about delta S of the universe here. This is the universe. They didn't specify which one it was, but as I read it more, if delta S is not positive, that's usually referring to the universe. They should have been more specific. Okay, same thing. They're saying the same thing again. Okay. You see, I've gone over it, so I know what's coming. Kind of. It's the same message, but in the picture. What's the message? Our goal is to make delta S positive. Look at this graph, right? Uh, the y-axis is showing you entropy. Entropy is going from a low entropy on the bottom to a high entropy on the top. So now we're going to examine what we have. We have a system that has negative entropy. You see that it's a huge number because it goes really deep, but it's negative. We have a surrounding that's positive because the horizontal line is at 0, right? So below it is negative entropy, above it is system has negative entropy, the surrounding has positive entropy. Add these two because the surrounding is positive and we end up with a net positive entropy of the universe. It's positive. All we need is positive. The prerequisite to be spontaneous is just a delta S of the surrounding that is positive. We don't need the value to be big. In this scenario here, the system starts off with a negative entropy and huge. Surrounding is positive, but small, right? It's small compared to the system. So when you add these two, the entropy of the universe is still negative and small. So this is going to be non-spontaneous. When does the left scenario occur? When you have positive universe, entropy of the universe, when the surrounding temperature is low, right? Surrounding temperature is low. Here, when do you have negative entropy of the universe? When the system is negative and the surrounding is positive, when the surrounding temperature is high. I'm like, oh my goodness, how many times have you made this point? It's important for them to communicate this to you. So, one of the ways I learned as a student what was important is how many times it was said. Because it's kind of like your parent, right? How many times have I told you to clean your room? Like 715. Why are you keeping count? But how often are they making this point? A lot. And then one more picture. I'm not gonna explain that picture. At this point, I'm like, listen, I got it. I got it. Okay, this has to be positive. Ah, okay. So then we move on to a new section, right? In this new section, we're talking about a different way of determining if a reaction uh, is spontaneous. Okay, so let's see. Oh, here. So we learn a new way. I like. So I have the recap over it. Okay, is the recap. Recap. We today, but I want us to recap again. What for a process to be spontaneous? This is what we learned before. Was stated way in the past. The first is a combo deal. They have to be together. You'll be given a balanced equation where the transformation delta H is given to you as negative. Okay? Delta S for that equation, transformation, whatever is given to you as positive. Just by looking at these two, you can conclude a process is spontaneous. Okay? That was the first scenario. Or if they didn't give you those first two, the next thing you're looking for is delta S of the universe. We just learned delta S of the universe has to be positive for a process to be spontaneous. Now it's like, I sound very repetitive, right? All of a sudden, it's not a lot of new information. All of a sudden, it's just the person saying the same thing over and over again, like a nagging parent, right? Only this is the author of the book and they're getting paid for this. Okay, so delta S of the universe has to be positive. Well, how do we get delta S of the universe to be positive? We have to examine delta S of the system, which is the reaction, delta S of the surrounding, which is, well, the environment. If both of these are positive, this is positive. If this is negative and this is positive and large, this still ends up positive. Okay? We just saw that. This is like the bottom line. This is now our newcomer to the criteria. Or, so now we have three options to pick from. If a question asks you to judge if a reaction is spontaneous, you are now armed with three possible ways to make that judgment. This last one that we're looking at right here, this is not the last of the last, right? But this is the one that we're looking at right now. It's called Gibbs free energy. So we want a change in Gibbs free energy, delta G. So when you're given delta G value, we're told here delta G has to be negative for a reaction to be spontaneous. So you're judging the reaction based on the thermodynamic quantity given to you, thermodynamic function. They could give you delta G, they could give you delta S of the universe, or delta H and delta S of the system, right? And then you have to judge based on the following criteria. Delta S of the universe is positive, delta G has to be negative. Okay, so if delta G is negative, we say the reaction is spontaneous. If delta G is positive, we say the reaction is not spontaneous. Okay, so what I want to do is I want to talk about this equation before I look at the next slide, because the next slide, which I skipped over, is actually this slide here. This slide here to me makes more sense when we've covered the other, the one that has the relationship. So the lab that you guys are working on next week ties into this lecture. Okay, Gibbs free energy and spontaneity. So Gibbs free energy, since we learned about what is it called? The entropy, right? Entropy is a measure of randomness. Entropy with a symbol S is a measure of random energy in a system. Okay? Gibbs free energy is a measure of a different kind of energy. So apparently, as we learned before, there's a bunch of different energies. People use the term, oh, low energy, high energy. You can be like, which energy are you referring to? Because there's a lot of different energies, but you don't want to be that person, right? So you want to just listen quietly and then extrapolate in your head. The Gibbs energy, Gibbs free energy, is, which is a symbol G, is the maximum amount of work energy that can be released to the surrounding by a system for a constant temperature and pressure system. So they're saying that when you're measuring Gibbs energy, G, you want to have the following environments: constant temperature and pressure. What are you measuring exactly? This is the work energy. Okay, but it's not the work, the energy essentially currently being used to work. It's the energy that's stored that can be used to work. Okay, so before I go back to the first definition, let me continue reading here. Gibbs free energy is often called chemical potential. Remember back when in 1411, yeah, 1411, potential and kinetic energy should have been defined. Potential energy is the stored energy. Okay, food is a potential energy because when you want energy, so to say, you eat food because you understand inside that food there's a lot of energy in calorie form, but it's a lot of energy, and when you eat it your body has the mechanism to harness that energy so that you can be more energetic. Okay, gasoline has chemical energy in the chemicals. Gas, what was it called? Octane, whatever. Octanol, octane, ethane, all the stuff, the chemicals they have in the gasoline stores a lot of potential energy, stored energy. Anytime we talk about potential energy, we're talking about stored energy. The way I related to this when I was learning this in middle school, I don't know, I was young, really young, was like savings account and checkings account. Usually you don't, you're not supposed to, okay, you can, but you're not supposed to just withdraw money from your savings account all the time. It's supposed to be saved, stored, right? Your checking account, you can go ahead and take out money as needed every day, all the time, as long as the money is present. So I look at kinetic energy as the checking account money, right? You're using it all the time. It's out there getting stuff done. And then potential energy is kind of like your savings account. So you have it for a rainy day, like an emergency fund for a rainy day, and you know it's there, and you know it's able to do stuff for you, but you're not using it, but it's stored and available. A battery will be an example of stored energy. It's just there. And when you need it, you harness it, right? So Gibbs energy is that measure, and people want to know how much energy a system can have that can be dedicated to doing work, right? Because not all the energy will be used to do work. Some of the energy is used to keep the system alive, right? If it's a human. So, so Gibbs energy is that measure, the maximum amount of work energy that can be released to the surrounding by the system. Okay? So here, once we understand that, we can figure out the change in the energy gives energy as the system is trying to work and release this energy, which is now being used to the surrounding. So the change in energy here of the system is equal to delta H of the system minus T delta S. So real quick, let's go ahead and recap the units of the system. I would say, in my experience, delta G is treated very similar to delta H. And you'll see as we go down the road in the chapter in my other video. Delta G is treated very similar to delta H. So the units for this, naturally, when you find delta G, is provided in kilojoules. Naturally, when you find delta H, units are provided in kilojoules. When you find temperature, units are provided in degrees Celsius. When you find delta S of the system, it's in joules per Kelvin. So you know how chemistry works, right? When you have an equation, you have to reconcile the units. The units have to be cancelable. That's not a word. I just made that up. I make up words. They have to be able to cancel to produce the desired unit according to dimension analysis. So when you're using this equation here, you will be solving for. So I'm going to start from the right to the left. You'll be solving for delta G of the system. Delta S will be joules per Kelvin. For this to work, temperature has to be converted to Kelvin, right? And then when you subtract this here, you see how Kelvin will cancel out. So that means that delta H of the system has to be in joules. And when you work this out, your answer will work out in joules. Now, once you get your answer in joules, you're free to then convert to kilojoules. Okay? All of these mathematical transformations have to be reconciled so that you know to calculate your answers correctly, right? And in your lab for next week, which I was hoping I was going to get to, I didn't get to it, but in your lab for next week, you would have to remember all of this and do the appropriate transformations, right? Joules per Kelvin, degrees Celsius has to be in Kelvin, this has to be in joules to get this in joules and then convert it to kilojoules, right? So this path here, very important. Okay, so to finish up this slide, since I've come this far, they're saying this because delta S of the universe determines whether a process is spontaneous or not. Delta G also determines spontaneity. Delta S is positive. Remember, delta S of the universe is positive. That means reaction is spontaneous. When delta G is negative. Oh. So when delta S of the universe is positive, the reaction is spontaneous. So they're kind of in a weird way saying the reaction is also spontaneous when delta G is negative. As I said, they communicate in a different way, a unique way. I shouldn't say weird. It's just different. Okay, different. Right. So I'm going to be going over, this is kind of where I left off on Tuesday. I'm going to be going over this part here. Actually, I just saved this to add to the recordings I have. In going over this, I'll go over this table first before I actually go over this slide right here. So let me actually take this slide here. Oh, it will help if I actually, I'll copy this slide and then repost it after that. I feel like it makes more sense in context after this. So where is this? I'm here. Paste. Oh, it came in after. Okay, what am I doing? Okay, I unintentionally brought it in after. So let me see. I meant to bring that in here. I delete this page. Delete that page. Yeah, I'm still trying to figure this thing out. Yes, okay. So here, I used some numbers. Now I kind of messed up here because on Tuesday, because I forgot to follow the rules. I wasn't following this rule very well. So what I'm going to do here is one of the things that you need to know. Yeah, okay. So what we're going to be doing here is coming to the same conclusions they came up with here, right? So their conclusion was what combination? So I'm paraphrasing this. What combinations of delta H, delta S, and T, what combinations provide spontaneity? I'm trying to find words myself. So after I criticize them with their words here, I am struggling with words. Spontaneity. Okay? We're trying to figure out the right combination of delta H, delta S, and T that will allow or provide for spontaneity. So I'll say allow spontaneity. What combination makes the process spontaneous? In this first condition here, you can see that, right? Delta H is negative, delta T is positive. Isn't that what we learned before? Uh-huh, it is. So what I'm going to do here, though, is to relate that to this equation we just saw. This equation we said earlier shows you how delta H, delta S, and T can provide for a spontaneous reaction. So what I'm going to do here is say for spontaneity, for a spontaneous process, delta G must be negative. Okay? So then what I did here was, I remember I was doing this on Tuesday, the other day. What I did here was I provided some numbers, right? And now I'm looking at this, I'm thinking I should have a really, really low temperature. Room temperature may not be low enough. Let me see, 273.15. 273.15. Clear. Oh my goodness, 273.15 minus 300. Oh, I guess that's what I got. Okay, same thing. So I'm going to try this out. I'm going to try assigning a value to delta H and assigning a value to delta S and assigning a value to the low temperature. I'm going to check out the left situation and see if I arrive in the same condition. Okay, so I'm going to work this over again. We're going to work this math out, saying if delta H is 10,000 joules, delta S is 100 joules per Kelvin, and then temperature is 26. Actually, let me make this a little bigger because the delta H's are usually really high. I'll make this, instead of 10,000, I'll make this 100,000. How about that? Delta S 100. Let's see, 1, 2, 3, so 100 kilojoules. That should be okay. No, I think the number I had was okay. Let's go with that. Yeah. If it doesn't work out, I'll just adjust it later on. So I'm saying if this is what we have, there's a H is this value, there's a S is this value, and then the temperature is 26.85 degrees Celsius. Okay. So I'm going to adapt these numbers for the first condition. In the first condition, I'm trying to examine what if the delta H is negative. So in the first condition here, since I'm starting everything from scratch, do we get a spontaneous situation? So in the first condition, H is negative, right? S remains positive, and then the temperature has to be a low temperature. So this will be classified as low temperature, and then for my high temperature, I selected the temperature, what was it again? Oh, 126.85 degrees Celsius. This is going to be classified as high temperature. So I'll use the second temperature whenever I am dealing with high temperature. The low temperature works out mathematically to 300 Kelvin. The higher temperature, when you add 273.15, works out to 400 Kelvin. So I would say, let me work this out versus just kind of rush to the answer. Plus 273.15 equal 300 Kelvin. And this is going to be low temp. Okay, plus 273.15. This is going to be 400 Kelvin, and this is going to be high temp. So I'm trying to recreate what's happening here. Low temp will deal with this number. High temp will deal with that number, okay? So let me go ahead and erase all this because I figured all those things out in this C. Okay, so we examine this scenario. This scenario says when the delta H is negative, delta S is positive, and the temperature is low, this combination will make the reaction spontaneous. So let's see if that works out with the numbers we have. Delta G is equal to delta H minus T delta S, okay? And the first scenario we're looking at, we said was what? Low temp. Okay, we're looking at low temp. So I'm going to plug in the numbers and solve for delta G, and then we'll decide based on the delta G value we get. Delta H has to be negative, right? Because it says so, delta H is negative. The negative here is going to be negative 10,000. So 4 zeros, joules, minus T. The temperature is a low one, so I'm going to use this number here. 300 Kelvin times delta S. Delta S is 100 joules per Kelvin. Okay, so let's work this out and see. Kelvin, oops, wrong thing. Kelvin cancels out, right? The top number becomes negative 1, 2, 3, 4 joules minus 3, 1, 2, 3, 4 joules, right? So this number minus that number, I get negative 4,000,000 joules. Delta G. Delta G is negative. Since delta G is negative, reaction is spontaneous. So in other words, when your delta H is negative and delta S is positive, the reaction is spontaneous. Oh, I need to specify this. At low temp. Oh, I almost forgot. At low temperature, right? Because remember, we tested this for low temperature. We're testing to see if it's spontaneous or not. So let's do the other test and test it for higher temperature. Okay. So our next move is same numbers. The only thing is this time we're going to be doing it at high temperature. So delta G is equal to delta H minus T delta S. Same numbers, only the difference here will be high temperature. So I have to use the second temperature. Delta G is equal to negative 10,000 four zeros minus temperature is higher, right? 400 K times 100 joules per K. The only thing that's changing here is the temperature. And the question we're trying to answer is, will this reaction be spontaneous or not at high temperature? At high temperature. My goodness, I can't talk anymore. Okay, so here, negative 10,000 joules. This times this, negative 4,000,000. K and K cancel out joules, so I'm left with negative 5,000,000 joules. Oh, look at that. Delta G is still negative, so it's spontaneous at high temperature. This is me shorthanding it. So in the world of thermodynamics, we kind of have low temperature and then we have high temperature. So by seeing this situation here, what can we conclude? When delta H is negative and delta S is positive, reaction is, it should be a small r, spontaneous at all temperatures. What do you mean all? We just showed that it worked for both low and high. And in the world of thermodynamics, there's only low and then there's high. I know they oversimplify things, but you know what I'm saying. So they say all temperatures. Sorry. I know I'm in the way. Okay, so that's kind of what they said here, right? So we did all this to explain this first row. So I'm going to read it from left to right. When delta H is negative, delta S is positive, and then we have low temperature, the reaction is spontaneous. Why? Because delta G is less than 0, meaning negative, right? Delta G is negative. Okay, what about at high temperature? At high temperature, with delta H being negative, delta S being positive, the reaction is also spontaneous. Why? Delta G is less than 0, meaning it's negative. All that math communicated that. Give us an example where this is true. You look over here and you're like, yeah, it's true, right? And the example doesn't really tell us much about the information because we're really using the numbers to conclude that. But in this example, look, we're going from 2 particles to 3. So you can see you have an increase in entropy. So this is positive, right? The entropy here is positive, and that's consistent at least with this sign right here. Okay. Now let's go ahead and examine the second scenario. In the second scenario, we have the same numbers. I'm not switching the numbers until they stop working. The second scenario, they said, is this the opposite of the first scenario? Yeah, it's the opposite. Haha, right, the opposite. Okay. So in the second scenario, delta H is positive, delta S is negative, right? Let me double check one more time. Yeah. Delta H is positive, delta S is negative. We're going to examine this for low temperature and examine it for high temperature. And then you see how it plays out. Wait, I'm trying to add a page. What did I just do? Did I just delete a page? Oh, I think I intentionally deleted a page. Can I go back? Oh, thank God. I meant to add a page, not delete a page. Add a page, add another page, add another page. Okay, same thing. Delta H, so I'm going to find delta G when delta H is positive. So this time it's 10,000, right? Minus the temperature, the low temperature was 300 Kelvin, right? I remember that. And then for the temperature, and then delta S has to be negative. Delta S was what? 100, yeah, 100 joules. 100, oops. Three zeros don't make 100. 100 joules per Kelvin. Okay. So all I'm doing is multiplying this out, and I'm going to get 10,000. Oh, I need to make this negative, and I have to follow the signs. If this is positive, and this has to be negative, this has to be negative. Okay, so when these two are negative here, we get 10,000 joules. Negative and negative make positive, plus 3 with 4 zeros. Okay, so when you add these two, what do you get? 40,000. The math is really not that bad. It's not that complicated. Look at what happened. Delta G is positive, not spontaneous. Not spontaneous at low temp, right? Because remember, this here is a low temperature. Okay, let's test this high temperature. So at high, let's see what happens. Conditions, H has to be positive, has to be negative. Let's see. Delta H, we're trying to find delta G, is positive 10,000 minus 300. No, this is high temperature, so it's 400. Man, I have to keep track of a lot of things. 400 K times negative 100 joules per K. Okay? Again, negative and negative make positive. So when you multiply this out, you get 4 with 4 zeros, joules, because this cancels out. And then 10,000 here. Doesn't matter. Positive 50,000 joules says not spontaneous, based on the sign, right? Not, or non-spontaneous, whatever, not spontaneous. Okay, so we can conclude if delta H is positive, delta S is negative, and the process is not spontaneous, whatever, spontaneous. My spelling is falling apart. I'm rushing to make a point. Spontaneous at all temperatures. I don't care what the temperature is because delta G is going to be positive. It's not spontaneous, just not spontaneous, nothing personal. Okay, let's go see how it was shown in the table. Okay, so when you reverse the starting condition, this is how I see, because remember I told you I'm a relational learner. I understood the first part, but how does the second part relate to the first part? Second part is exactly opposite to the first part. So when I was a student, I memorized this first part and then used logic to recreate the second part. The second part is exactly the opposite to the first part. So this is now positive, this is negative. So you get the opposite response, right? Non-spontaneous at low temperature, non-spontaneous at high temperature, right? That's what it's saying because delta G is positive. I showed you how it worked out. it would be like you trying to convert oxygen to ozone. Yeah, that's sad. If this was spontaneous, then oxygen can be converted to ozone. Well, you know what? I take it back. I was being short-sighted. This is a good thing. I just thought about it. I'm like, wait, we breathe oxygen. If our oxygen was being used to convert to ozone naturally, the oxygen in the universe will run out and then we'll die. Okay, so this is a good thing. I changed my mind. That was so quick, man. Yeah. It is sad because the ozone layer does protect the earth from the sun rays, but it's a good thing that this is not spontaneous. We don't need this to be happening out of our control because then the oxygen will run out and then all life will cease to exist and that'll be the end, right? So what I'm going to do is I'll only work number 3 and I'll extrapolate to number 4 because remember, if you look at the conditions right here, number 4 is the opposite of number 3. So I kind of, when I was studying this as a student, I'm like, oh, this is hard. Then I was like, wait, I get it. I really just really have to understand number 1 and number 3, then apply it to the number 2 and number 4. Okay, now we need delta H and delta S to be negative, right? Both of them be negative. And somehow that will produce a spontaneous, and then the second scenario, non-spontaneous. Hope this works out. Let's see. Okay. So now the conditions are delta H is negative, delta S is negative. And our first scenario is low temp. That was the 300K, right? 300K. Okay, so delta G here is equal to negative 1 with 4 zeros, 10,000, minus 300 Kelvin times negative 100. I have to write it slowly. I've met that condition, I've met that condition, I've met this condition. Joules per Kelvin. It does get tricky when I start doing all this. This and this multiply to give me a positive, so positive 3 with 4 zeros, 1, 2, 3, 4 joules. And then this is negative 1 with 4 zeros, joules. Okay, when we add these two numbers, oh, these numbers are not working out. Remember I told you that I'll try these numbers and if it works out, okay, let me just drop this zero from here and then it will work out. Because I'm just making up these numbers, but in reality, these numbers, the delta S has a certain magnitude, and you see that during your experiment. So this one, let's say 10. That's all I'm going to change here is 10. Because I know it has to work out to be spontaneous. So for it to work out, we can lose 1 0 here. That's all I'm going to do. Same process, only I'm using a different value for S. S will now be 10 joules per Kelvin. It should work for the other one too. And then H will be 10,000. Okay, so this would be 3,000, right? So negative 10,000 minus 3,000 gives us negative 7,000. Did I just make up the numbers? Yes, I did. These were made up numbers. I didn't pick very good quality made up numbers. Delta G is going to be positive. I mean, sorry, negative. Therefore, the reaction will be is spontaneous. Okay. I tried the same thing, but this time at a higher temperature. So I really do hope this works out. The good thing is you guys don't, I mean, you guys do have access to that table, so you can just memorize the table. That works too. When I was in school, I just memorized the table. And I had the math part as a backup. I will use the numbers given to me in an exam to recreate this scene. So the numbers in the exam will be more correct because they're based on experiments. I literally just pull these numbers out. Okay. So let me see delta G if it works for the high temperature one. Negative. So this is high temp. Negative 10,000. I should have selected numbers from a question. Anyway, and this is minus 5. No, it's 400, right? No, I'll go with 500 times. This should still be negative. I know this is so with this one here, I'll go back to using the 100 joules per Kelvin. I know I'm doctoring the numbers because I didn't use very good quality numbers. So right here how This times this, multiply out, and you end up with 5,000 here, or not 5,000, sorry, 50,000. This number is bigger than that number, and you end up with a positive value. Bottom line here, when you add these two, you end up with 40,000 joules, just joules. And this is showing you this is going to be non-spontaneous. I did not pick very good numbers. I did this very well one time, but I've forgotten what numbers I used. Bottom line here is when you have this combination, and you can memorize that, because in those MCAT, PCAT exams, they could easily ask you this kind of question. If you have a scenario where both delta H and delta S are negative, and you have a low temperature, that combination provides spontaneous. Then high temperature provides for non-spontaneous reaction. Example here is freezing water, right? Freezing water does not happen naturally at high temperatures, it happens at low temperatures. Then when you look at the opposite scenario, where delta H is positive, delta S is positive, at low temperatures you have non-spontaneous process, high temperatures will be spontaneous. Example here is boiling of water. So you can boil water at a high temperature, but you cannot boil water at a low temperature, right? It happens at high temperature, not low temperature, right? And that's it for as far as today is concerned. I feel like I've done a lot of talking, but bottom line here is you have to understand what this table is showing and what it communicates, because it's important for you to know what these symbols produce. So I think I may have some homework questions where I'm asking you, if you have this combination here and that combination and low temperature, does it produce a spontaneous or non-spontaneous reaction? You want to use this table to figure it out. You don't have to use all the math unless they give you numbers. And do not despair. The numbers they give you in the homework, they would have been tested numbers based on experiments. I just pulled up numbers, and you can tell they weren't very good numbers because they worked in certain conditions but not others, right? So the numbers they use will be based on actual experiments, which will end up working with this table a lot better than my numbers did. Okay, but I did try to follow the conditions they provided. But yeah, that's it for this table. So the rest of the lecture should be recorded. I am going to post this one too, but oh, I added so many pages. Yeah, this everything we saw here is summarized in this table here. The one thing I would say, so this to tell you, of course, if delta H is negative and S is positive, meaning exothermic and more random, then delta G will be negative, and the reaction is going to be spontaneous when you have those conditions. And then we're told here when delta H is negative and large, and delta S is negative but small, also the reaction is spontaneous. So these are just different combinations, right? Delta H is positive and small, delta S is positive and large, or high temperature. This reaction is spontaneous. So I feel like when you're just reading it, it seems meaningless. It makes more sense in the context of the table. One thing that wasn't mentioned in the table is this part here. When delta G is 0, the reaction is at equilibrium. So delta G being negative, less than 0, is spontaneous. Delta G being greater than 0 is non-spontaneous. But delta G being equal to 0 is equilibrium. Okay? So from here, I'll say start here just in case. On the slides, we ended up here. Now, theoretically, I do have the rest of this chapter already posted on eCampus, so you can go ahead and continue reading the rest of it. At some point, I will try to work on the lab and record that after I take a break. But that's all I have for today. I know it was a lot, but yeah, that was it. It's taken a lot out of me. I feel like I've decreased in energy and thereby entropy a little bit, but yeah. Let's see. Do you have any questions?
No, I don't. Thank you.
Okay. You're welcome. Have a nice weekend.
Thank you. You too.
Okay, bye. Where's the stop button? Oh.